Assalamu alaikum students, welcome to the lecture number 9 of Advanced Nanomagnetism. Today we will learn about Stoner-Wohlfarth model, which is also very useful for finding the hysteresis of nanoscale materials. The Stoner-Wohlfarth model of ferromagnetism is the simplest model to describe the magnetic properties of small nanoparticles, which are single domains. The model is first theoretically described by Stoner-Wohlfarth in 1948. This model demonstrates how the anisotropy present in the system can lead to hysteresis and how it depends upon the angle of magnetization and so on. It is particularly interesting to note that over 50 years of its original development, still it is useful. Although the original study of Stoner-Wohlfarth model assumes shape anisotropy only, now it is widely used for the uniaxial magnetic crystal anisotropy, which we already know from the previous lectures. The main assumption of the model is that the material is made of fine particles, or the small particles, and they are non-interacting, sufficiently separated from each other. The Stoner-Wohlfarth model is a widely used model for the magnetization of the single domain ferromagnets. It is a simple model to find out the magnetic hysteresis and useful for modeling small magnetic nanoparticles, which can be used for magnetic data storage in biomagnetism and rock magnetism and so on. It included a numerical calculation of the integrated response of randomly oriented magnets. So if we go deeply in the model, let us we have a magnetic field, applied magnetic field, and angle theta to easy axis of the uniaxial anisotropy of the particle. The magnetic vector will rotate to an angle psi from the field direction. So the total energy of the system will be given by equation 1, in which the first term includes the k1 v and sine square of angles, and k1 is the anisotropy, effective anisotropy constant of the material, and it is related with, this term is related with the anisotropy of the material. The second term is the gives the information about the interaction of magnetic moment with the applied field H. So here V is the volume of the particle and mu is the magnetic moment. Ms is the saturation magnetism of the bulk material. So SW model preferred to work with the reduced energy. In this model is reused the reduced energy, which is shown in the above equation, in which H is equal to Ms capital H over 2k V, which is also reduced field. For the given values of theta and H, the magnetism vector will choose the angle psi, which minimize the energy function in above equation, such as we have to put the derivative to 0 and the second derivative should be greater than 0. The first condition gives us this first equation, and the second condition, if we take the double derivative, and it will give us the second equation. If this second derivative is negative, the equilibrium is unstable, and if the second derivative is 0, the condition of stability is just changing to one of the instability. The field at which the instability of the magnetism occurs is known as the anisotropy field, and he calculated this anisotropy field equals to hk is equal to 2k over ms, and due to this anisotropy field, you can have the hysteresis in your model. And in Stone-Wohlfarth model, this anisotropy or shape of the hysteresis loop has strong dependence on the angle between the magnetic field and the z-axis. You can see with the change in the angle between magnetic field and the z-axis, the coercivity is changing very quickly from maximum to zero coercivity. Some hysteresis loops predicts by Stone-Wohlfarth model for different angles between the field and axis is shown in this figure, which is between reduced applied field and magnetic moment. So if the two are parallel, means two vectors are parallel, the theta will be 0, the hysteresis loop at its biggest, and the magnetism starts parallel to the field and does not rotate until it becomes unstable and jumps to the opposite direction. On the other hand, extreme position, when the theta is 90 degree perpendicular with the field perpendicular to the z-axis, no such jump occurs. So magnetism rotates continuously from one direction to another. And Stone-Wohlfarth also calculated the main hysteresis for isotropic system, in which we have small particles randomly oriented magnetization, which is very close to the practical system. And if we add up all these curves, which from zero angle to the maximum angle, the result of the calculation is reproduced in the right figure, which is very useful for simulating the nanoparticle system or which are oriented randomly, and is still very useful in the to find out the different parameters, such as the effective anisotropic constant of the nanoparticle, the ferromagnetic nanoparticle system, and also the coercivity, and also however, the restriction is that the interaction between the nanoparticles are not included in this model, and there are some modifications suggested in the literature about this model. Thank you, students. Goodbye.